Alright, Earth science enthusiasts, let's chat about a fascinating element that you might encounter in the crust we all know and love, Mercury. Often dubbed quicksilver or watery silver thanks Greeks and Romans. Mercury is a bit of an oddball in the periodic table. It's right there with all the other solid, respectable metals, but at room temperature, it's just, well, liquid. Imagine trying to build something out of liquid metal. It doesn't exactly lend itself to sturdy structures. And yet, Mercury chills out in its liquid state while its metallic buddies like copper, silver, gold, and even its close neighbor thallium are stubbornly solid unless you crank up the heat to hundreds or even thousands of degrees Celsius. For ages, chemists scratched their heads about this. Why was Mercury, a heavy metal, behaving more like a gas than a typical metal? They knew it had a low melting point, but why was that melting point so low compared to other metals? Just stating it is low doesn't explain the reason behind it. Turns out, the secret to Mercury's liquid nature isn't just in its chemistry, but deep within the realm of physics, specifically Albert Einstein's special theory of relativity. Yes, you heard that right. The same theory that explains things like time dilation and the equivalence of mass and energy also helps us understand why Mercury is a liquid at room temperature. Who knew geology and cosmology were so intertwined at the elemental level? Okay, maybe not cosmology, but certainly fundamental physics. So, how does relativity factor into the life of a tiny Mercury atom? Well, it's all about the electrons. A Mercury atom is pretty beefy, with 80 protons in its nucleus. This large positive charge exerts a strong pull on the electrons orbiting it. The innermost electrons, especially those in the s orbitals, are pulled in very tightly and whiz around the nucleus at incredibly high speeds. We're talking speeds fast enough that they approach a significant fraction of the speed of light. And when things move that fast, relativity kicks in. According to Einstein's theory, as an object's speed increases, its mass effectively increases relativistic mass increase. This increased mass affects the electron's behavior and the shape of its orbit. Specifically, for these speedy inner electrons in heavy elements like Mercury, the relativistic effects cause the orbitals to contract. Think of it like a very fast-moving planet getting pulled closer to its star. Though the analogy isn't perfect, it gives a little visual. This orbital contraction and the associated changes in energy levels due to relativity have a cascading effect on the outer, or valence, electrons. In Mercury, the outermost electron shell is full. This already makes the electrons less eager to jump ship and form strong bonds with other atoms compared to metals with partially filled outer shells. But relativity adds another layer to this reluctance. The relativistic contraction and stabilization of the inner s orbitals influence the outer electrons, making them even more tightly bound to their own nucleus. They become quite content staying right where they are, associated with their individual Mercury atom. This means that the outermost electrons in one Mercury atom don't readily interact with or get shared with the electrons of a neighboring Mercury atom. Unlike most metals, where valence electrons form a sort of shared electron sea holding the atoms together in a strong metallic bond, Mercury's electrons are more like solitary introverts. The forces holding individual Mercury atoms together are therefore much weaker than the strong metallic bonds found in solid metals like gold or copper. Instead of robust metallic bonds, Mercury atoms are held together by weaker, temporary forces, like van der Waals forces. Because these interatomic forces are so weak, it doesn't take much energy to overcome them and allow the atoms to move past each other. At typical room temperatures, the random kinetic energy heat of the Mercury atoms is already sufficient to break these weak bonds. Think about trying to hold a bunch of marbles together with sticky tape versus trying to hold them with strong glue. It takes a lot less effort to separate the marbles with sticky tape. Mercury atoms are like the marbles with weak sticky tape. So, while other metals need a lot of heat energy to increase the kinetic energy of their atoms enough to break the strong metallic bonds and transition to a liquid state, Mercury needs very little. Its melting point is already below typical room temperature, meaning it's happily liquid under normal conditions. This unique property, being a dense liquid at room temperature, is a direct consequence of how relativity affects the behavior of its electrons, weakening the bonds between individual Mercury atoms. For you geologists out there, this property does have some cool implications. Because the elemental mercury HgO is so volatile due to this weak bonding, it can easily evaporate and form mercury vapor. This vapor can migrate through soil and rock. It can even form detectable halos above buried mineral deposits or geological faults. Scientists can measure this mercury vapor in the near-surface air to help locate these buried structures. It is a neat trick where the fundamental physics determining Mercury's state at room temperature links directly to a geological exploration technique. This ability to form mobile vapor is a direct manifestation of those weak interatomic forces we talked about, themselves a result of relativistic effects on the electrons. So, the next time you encounter Mercury from a safe distance, perhaps in a historical context like an old thermometer, remember that its unusual liquid state isn't just a random quirk. It's a fascinating demonstration of how the fundamental laws of physics, even something as mind-bending as relativity, influence the everyday properties of the elements that make up our planet. It's a little bit of deep space-time physics showing up right here on Earth's surface.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.